Welcome back to the classroom. My name is Mr. Wong, and we're going to look at another physics exam problem. This one will be related to conservation of energy in satellite motion, which will be quite a good one. This will be Module 5, Inquiry 3. So this is question 25. We have a rocket that is launched vertically from a planet of mass m. After it leaves the atmosphere, the rocket's engine is turned off and it continues to move away from the planet. From this time, the rocket's mass is 200 kilograms. The rocket speed v at two different distances from the planet's center r is shown. So we can imagine we have a rocket and it was launched at two different positions, and then the distance to the center given as r. Question A, it says show that the magnitude of the change in kinetic energy from point 1 to point 2 is 2.2 times 10 to the power of 9 joules. Okay, so what we know is the change in kinetic energy is equal to the final minus the initial. So point 2 is obviously the final point, and point 1 is our initial point. So we'll have the kinetic energy at 2 subtracted by the kinetic energy at 1. In terms of what formula we need to use to find the kinetic energy, you can use half mv squared. So half mv, we'll call this 2 squared subtracted by half mv 1 squared. So 1 would obviously be the 500,000, and then obviously V2 would be the 2,900. So we just do that writing out there, and then we can do our substitution shortly. So from here, I find that the answer is negative 218400000. And if we actually have a look at these values here, this is looking at the magnitude, so it doesn't really matter about the negative sign here, but what we can write is, as a consequence, if we round it off to two significant figures, it is 2.2 times 10 to the power of 9 joules of energy. The reason why it's negative is because that energy is being converted into gravitational potential. So I'll just write that down just for those interested. Negative as Ke transforms into gravitational potential, and probably other forms of energy like sound, light energy, and so on. That completes the first part of the question, and we go to question 2, which states, or which asks us to determine the mass of the planet using the law of conservation of energy. So what we're trying to say with the conservation law of energy is any changes in the total energy is always conserved. So the total change in energy is equal to 0. And the reason why it's 0 is because the change in kinetic energy plus the change in gravitational potential energy will always cancel each other out. So if I have lots and lots of kinetic energy, I'll have a small amount of potential, and then if my potential increases, my kinetic will therefore decrease. So that's the situation we have here. We calculated the change in kinetic energy to be 2.2 times 10 to the power of 9 joules. And what we can use is the change in gravitational potential to find the value of mass. So what I can rearrange here, see how this equation is 0 on this side. Let's move the value for gravitational potential over. So gravitational potential, the negative sign of the change in gravitational potential is equal to kinetic energy. And I know that that change in kinetic energy is the value that we found before. Okay. So we can use the gravitational potential formula, Gmm over R negative, or you could use the kinetic energy formula, to find out the radius or the mass of the planet, sorry. We're going to use the potential formula, more so because it's already on the data sheet and it's one that probably most people will be able to recognize rather than our kinetic energy formula. So let's have a look at how to solve it using this equation here. Okay, so for our convenience, let's just say the change in gravitational potential as a positive value is equal to the change in kinetic energy, which will be, for our own sake, a negative value. So therefore the value that we got, a positive value there. If I rearrange the formula, I'll write down what formula we want to try and use, and then we'll do our substitutions from there. Just for our own benefit, I'll use delta U to represent change in potential. So we have change in U equals to the final value of our potential minus the initial value of our potential. The formula we're using is Gmm over R negative, negative for this negative sign here, and then negative again for Gmm R here. This is the final point, which, as we said before, is just number 2, and then the initial point, which is number 1. And then we have delta U. You can see here that capital G, lowercase m, are constants. Those numbers don't change. So we can actually try and make things a little bit easier for ourselves if I just rearrange this equation a little further. So just write it like so. Okay, so it's a positive value that we have here. If I move the values out, so I have G and little m, or big M and little m, becomes the following formula. I'll leave this value as it is. We might even want it as a negative value overall. We'll see. All right. So the final radius in this case here is 2.5 times 10 to the power of 7, and the initial radius is 4.3 times 10 to the power of 6. It's quite a lot of working out here. So let's just write the number over here. You could write it in scientific notations as well. Probably will do that later on. Just down here, times 10 to the power of 9 equals 2. And you can see I've used the complete value instead of the rounded off value. That would be the best. That would give you the most accurate value for m. So negative 6.6 times 10 to the minus 11 times 200 m, and then we have our radius values. And that's what we have. If we then expand the brackets out, if we find what the values are, the value that we have here becomes negative 1.334 times 10 to the power of negative 8 multiplied by m, and these two values here become 1.9255 times 10 to the power of negative 7, and that gives us a value of negative 2.568617 times 10 to the power of negative 15 multiplied by m. Just leave that as a negative value there, so 2.184 to the power of 9. And then hopefully you can see what I'm trying to do here. I'm going to divide the two numbers across to find my value of m. So m in this case, and you probably don't have to do as much working out as I've done here, but it's just to make sure everyone's on the same page as I am in regards to what the procedures are. Okay, so once we do that, I'll write you the full answer, and we can also write down the rounded off answer as well. So the final answer should be 8.502630015 times 10 to the power of 23 kgs. If we look at the smallest significant figures we use in this equation, it is 2. So we round it off to 2 sig figs, which is 8.5 times 10 to the power of 23 kgs. So that would be the mass of the planet in which the satellite was launched in. Hopefully this video has answered your question regarding how we could solve problems related to changes in kinetic energy and potential energy, and how we relate that to satellite motion. If you liked the video, like, and if you haven't done so already, subscribe, and I will see you next time.